Just think about it for a second. A machine that's hundreds of tons of steel and aluminum carrying hundreds of people, and it's slicing through the countryside at 300 kilometers an hour. High-speed rail, it's not just fast, it's a genuine masterpiece of engineering. But it all begs the question, how do you make something that powerful, that fast, truly safe? Well, let's dive in and find out.
And you know what's so amazing is that the challenges that come with this kind of speed, they aren't new. This right here, this is the cover of a report from the U.S. Federal Railroad Administration from 1993. The very questions they were asking back then about how to avoid collisions, how to make a train survivable in an accident, those are the exact principles that make today's high-speed trains so unbelievably safe.
And that really is the heart of it, isn't it? I mean, when you have that much mass moving at that much velocity, the amount of energy involved is just astronomical. So how on earth have engineers built a system that can actually tame that power?
So here's how we're going to break it down. We'll start with the high-speed challenge itself, and then look at the anatomy of a collision. From there, we'll explore this kind of two-layered fortress of safety. First, collision avoidance, and then accident survivability. And finally, we'll see how it all comes together.
Okay, so first things first, we have to appreciate the physics of it all. It's really easy to just sit back and admire the speed, but for the engineers, they have to obsess over the risks that come hand in hand with it. You see, the core of the problem is kinetic energy. In a collision, or even just in a really sudden stop, all of that incredible energy has to go somewhere. The entire goal of high-speed safety design is to figure out how to control and dissipate that energy in a way that protects human life, no matter what.
To build a safe system, you first have to really understand what you're protecting it from. So, what are the big threats? What are the scenarios that keep railway engineers up at night?
Well, that Federal Railroad Administration report breaks them down into three main categories. First up, you've got train-to-train collisions, and these are the most dangerous by far. Second, there are train-to-obstruction incidents. That could be anything from a truck on a crossing to a rock on the line. And finally, you have single train events, like derailments. And the data makes it crystal clear why that first category is the absolute top priority. While other things can and do happen, it's the train-to-train collisions that have the highest potential for a truly catastrophic loss of life. So preventing them is job number one for the entire system. So, let's look at that first layer of our safety fortress, collision avoidance. You can think of this as the proactive, intelligent system that's designed to make sure two trains never, ever try to occupy the same space at the same time. It's like an invisible shield. At the very heart of this shield is a system called Automatic Train Protection, or ATP. Think of it as a digital guardian angel. It knows the track ahead, it knows the speed limits, it knows where all the other trains are. And if a human operator makes a mistake, or for whatever reason fails to respond, the ATP system will automatically apply the brakes. And here's the key, it can't be overwritten. What's really cool is seeing how different systems do this. The German LZB system, which you see here, is in constant communication with the track itself. It's continuously calculating a maximum authorized speed for the train, creating this dynamic, moving safety bubble. If the train's actual speed even touches that authorized speed, the system steps.
Now, the French TGV, it takes a slightly different approach. Its system calculates the exact braking curve needed to stop before the next signal. So in the cab, you'll see a speed limit, sure, but there's also this invisible, slightly higher trigger speed. If the train exceeds that speed, it means it can no longer stop in time using normal brakes, so the ATP slams on the emergency brakes. Two different methods, but they both have the exact same goal, a guaranteed stopping distance.
But hey, collision avoidance isn't just about the train's brain. It's also about locking down its entire environment. This means completely fencing off the railway, getting rid of road crossings on all new high-speed lines, and even installing sophisticated detectors for, well, everything. From earthquakes in Japan to cars that might fall off an overpass in France.
And all of that data, every single sensor, feeds back to a central control room, just like this one for the Japanese Shinkansen. This is the nerve center, the human-machine interface, where dispatchers are watching the whole network. They're ready to respond to any alert, whether it's a high wind warning, a track circuit failure, or an earthquake detection.
So, what happens if the unthinkable occurs? What if, somehow, all of those avoidance systems fail and a collision is about to happen? That's where the second layer of the fortress kicks in, accident survivability. And this is all about pure physics and brilliant structural engineering.
The easiest way to think about it is to think about your car. Collision avoidance systems like automatic braking and lane assist, that's the train's ATP.
They're trying to prevent the crash from ever happening. But accident survivability features, airbags, seatbelts, crumple zones, they're there to save you when the crash happens.
This slide shows a really fascinating contrast in safety philosophy. The old-school North American approach demanded immense buff strength. Basically, you make the train a rigid battering ram that could withstand 800,000 pounds of force. But the European approach, which has really become the global standard, it's a totally different way of thinking. It's a shift from brute strength to intelligent energy absorption. The idea is to design the train to sacrifice parts of its structure in a controlled way, just like a modern car's crumple zone, to protect the passenger cabin at all costs.
And here is a perfect example of a survivability feature in action, the TGV's articulated design. See, instead of each car having its own set of wheels, adjacent cars actually share one. This creates this semi-rigid link that makes it incredibly difficult for the train to bend and jackknife during a derailment. And that jackknifing is a huge cause of casualties in conventional train accidents. This train is literally designed to stay in a straight line even when things go very, very wrong.
So the crucial point here, the big takeaway, is that high-speed rail safety isn't about one single magic bullet. It is a comprehensive, deeply integrated system of systems. You've got the intelligent, proactive systems that are always trying to prevent an accident, and then you have the robust, reactive systems designed to protect passengers if one does happen. It's this defense in depth, this combination of layers, that has created one of the safest ways to travel on the entire planet.
And look, you don't have to take my word for it. Let's just look at the data. This chart compares accidents per billion passenger kilometers. Now, you might glance at this and see that rail has more all accidents than airlines, and that includes very minor stuff. But look at the crucial bar, the one that really matters, fatal accidents. The rate is just extraordinarily low.
And what this really proves is that the system of safety, it works. It works exactly as it was designed to. It is exceptionally good at preventing the most severe, high-fatality events, which is, of course, the ultimate goal of all of this incredible engineering. But all of this does raise one final big question. As we keep pushing the boundaries of speed, I'm talking 400, even 500 kilometers per hour, with new maglev and rail technologies, how will these layers of avoidance and survivability need to evolve to manage even greater energies and even smaller margins for error?